Hello, this is Aaron, and I'm going to be doing problem one for March 10th's recitation. So let's just jump into it. So the first problem has to do with two small cats, Lucky and Matilda, and they are sitting on a table that has some friction associated with it, and we start to tilt the table, and we're interested in the point where right around the point where it's the tilting angle becomes such that they will start to slide, as we'll see later on in this problem. So let's start out by drawing a cartoon of the situation. So we draw our table, we can draw it like so, and it's at some angle, so we can draw that like this. And we draw our angle, theta, theta, like this. And we put our cat right on the table. So let me draw a cat. Let's see here. Its ears, whiskers. Okay. Okay, so we have our cat on the table, and we are now going to draw the force diagram for this cat. So we'll just draw it like this. We'll put a circle, and we could put some whiskers in here, why not? Okay, so we have our cat, and so for the forces, we have gravity pointing down. We'll write this as a vector. We'll soon see why it's nice to write these things as vectors. So one thing I didn't do right away, but we should do, is think about our coordinate system. So in this situation, it's going to be advantageous to use a tilted coordinate system, where if we have our table, we can write our coordinate system tilted such that our y-axis is now pointing this way, and our x-axis is pointing this way. So this is the x and the y. Had that backwards. Y, x, and this will make our problem a lot simpler. So now let's go back to these forces. So the reason I thought about it at this point is because we have to draw our normal force perpendicular to the table. And it's nice because it's going to be in the direction, it's only going to have a y component. So we can draw it like this. And this would be the normal force. And this is going to depend on theta, as we will soon see. And we're also going to have a frictional force, which is, we can think about the direction of the frictional force because it's going to oppose the direction that the cat would slide if there were no frictional force. And it's going to be right in our x coordinate. It's going to only have an x component. And it's going to go like something like this. So that's nice. Okay, so now that we have our forces, let's move on to writing out Newton's second law. But first we're going to need to think about the components of the normal force or the gravitational force in our coordinate system, because we're going to need that when we write these vectors in terms of our coordinate system. So let's do that. Let's write out a little arrow for our x-axis, and then we can go back to the force of gravity. So it's going to have some component that points positively along the x-axis, and that's going to pull us down, and that makes sense. Or pull the cat down. And then we're going to have a component in the along the y-axis, which is going to look like, this. So these two vectors added together give us our gravitational force vector. And now we have to think about where does theta go. So we know theta is this angle. So that basically means that the x-axis was tilted to the right, an angle theta, off of the from its original position. So we can do that same logic for the y-axis, which is this way. The y-axis was tilted an angle theta this way, which means that this angle is theta. And this is how we get our angle theta in our triangle. So now that we have that, we can move on to our next problem, which is writing down Newton's second law. So let's do that now. So Newton's second law, you can write it out. So we have sum of forces. So this is just so we have the friction force plus the normal force plus the gravitational force. So now we can write these out as vectors, like so. Do right. So the frictional force only had a component in the negative x direction. So we can write that out as such. And we know the frictional force is proportional to the normal force, so we'll put that in now. So if we write the absolute value of the normal force as Fn, then we can write minus mu Fn, where I left no subscript on mu because we don't know if it's the kinetic friction or static friction yet. So we can write that vector. The zero component is in the y direction. So now for the normal force. So that looks like only something in the y direction. So that's easy, and we'll just write that in as Fn. So 0, Fn, and then we have the force of gravity. So using some trig, we know gravity is mg, and then we need to think about the components. So the x component is going to get a sine theta, it's the opposite side, and the y component is going to get a minus cosine theta. So we can write that like mg sine theta and minus mg cos theta. Okay. Now this is going to equal ma, but we're going to write ma like m times this vector ax, ay. Okay. So now this is nice because now we can think about ax and ay individually, and we have our two equations. We have our x equation upstairs, and we have our y equation downstairs. But let's think about ay for a second. So our cat, we can assume, is not accelerating through the ramp or the table and is not accelerating upwards away from the table. So that implies that ay is 0. Erase it. Oh, that's a big eraser. Put that. I'm going to do 0. So that's nice. So we can condense these two equations, and we'll write that right down here. So down here now we have minus mu Fn plus mg sine theta is equal to max, and Fn minus mg cos theta is equal to 0. Okay, so nice. So now let's go on to this next question. So right before the cat begins to slide off the table, what's true? So at that point, it's right before it's sliding, so we can say acceleration is 0. That's the x acceleration, so that's good. And what about the frictional force? Well, the frictional force is static friction, so we're going to be using our mu-s coefficient from above. And we were given numbers for these for the different cats. I'm not going to plug in numbers. I'm just going to work for the algebra, and we're going to see that it's going to be very simple to plug numbers into a calculator, but that's not something I'm going to do. So let's write out this in the y equation. So we can easily solve for the x equation. In the y equation, we have Fn. We can find Fn. Fn is equal to mg cosine theta. So that's nice. So now we can plug that into the x equation, which we just said the x acceleration is 0. So that means minus mu static now, Fn mg cos theta plus mg sine theta is equal to 0. Okay, so let me move that equation up here so I have some room. So that's nice. So then we can write here, we can factor out an mg and cancel it with the 0, and we're left with, and if we move around mu s, we move this term to the other side, then we're left with, well, let's just do that right now. We'll just write it like this. We'll just go, we can cancel these out, and then we can erase the 0, equate this, moving this, adding this term to both sides. We can equate this and make this a minus sign. And then if we divide sine by cosine, then we get mu s is equal to, sine over cosine is tangent, tan theta, which implies the angle, which I'll call theta star, the angle that our cats slip at, and is equal to arc tan of mu s. So I'm not going to plug these numbers into my calculator, but you can find theta for each cat because we're given mu s for Lucky and Matilda, and you can plug those in the formula. And this doesn't depend on mass, so you don't even need to worry about it, and you can find the theta for each of those. So let's put that in a box. So we can do, oh, let's make this a blue box. Oh, not very square. I want it to be square. Apparently I'm not good at drawing squares in today. There we go. So that's nice. Theta equal to arctan of us. Okay, so now we're worried about what happens right after Matilda begins to slide. And right afterwards, she's going to start to accelerate in the x direction. So she's going to start sliding down the ramp. And now since she's moving, we're going to be worried about the kinetic coefficient of friction. So let's write out our x equation now and plug in our mu k. So we can write that out. We have m a x. Let's write that again. MAX is equal to, let's plug in what we know. So we have minus mu kinetic mg cos theta, normal force, plus mg sine theta. Okay, so we have m's across the board, so we can cancel those out, and we can pull out a g, and then we're left with ax is equal to g sine theta, we'll write it over here, sine theta minus mu k cos theta. And this is the theta where, right at the point where it began to tip. So that's theta star. Put that in parentheses. So what you're going to have to do is find theta star for each cat. Find theta star for each cat and plug it in to, oh gosh, I lack the ability to draw squares today. One last attempt. That's good. Okay, so you're gonna have to find theta star for each cat and plug it in to here. Still in square mode. Okay, so with that, you'll be able to find the acceleration, the x direction, and for each cat. So taking a look at this, so this graph of the frictional force over time versus tilt angle. So let's decipher this. So what this is telling us is that as we start to tilt, so down here we're at theta, this is theta. So we're at theta equals 0. And at theta equals 0, friction doesn't need to do anything to keep the cat stationary. So that makes sense. And as we start to increase the angle theta, our force of friction required to keep the cat stationary starts to increase up until the point where we reach our theta star, the point where the cat slips, which we found earlier. And at that point, we switched from static friction to kinetic friction. So there's this jump, this discontinuity, where we switch down our force of friction, the coefficients change, we go down to kinetic friction, and we start to decrease. So as we get further and farther to the right, we increase the angle greater and greater. We need less and less. The force of friction becomes less and less because we'll start to accelerate faster and faster. So, or rather, not accelerate. We'll start to accelerate faster and faster, but rather the normal force will be less and less as we get farther to the right. So the friction is proportional to the normal force, which gets less and less. So we decrease. The friction force decreases as we get to this. And if we go all the way down to 90, we track this out, it's going to hit the ground, or it's going to hit the floor where there's no force of friction because we totally just fell off the table. So that's it for problem 1.